Hello everyone, welcome to the Geo-Files. Today I'm going to be talking about plate tectonics because you all wanted it, and it's going to be a long one, so brace yourselves. Also, it is thunderstorming out when I recorded most of this. It's really hot in here. This boom, sky booms. Anyway, it was really hot out and I had the air conditioning running. It was also raining. I'm filming this as the very last thing because I wanted to give you guys a good introduction about what I'm going to talk about here. And in a minute you're going to see me with 4 points, which I'm going to cover throughout this lecture. I do have graphics this time for you. It's not just going to be me talking at you. And I am going to talk about plate tectonics, and this book is one of my favorite books. It actually is from the 1990s. Not much has changed about our understanding of plate motion anyway. And I'm just going to show you this little bit inside, but I'm going to talk later about Euler Poles, and you're going to hear me talk about this stuff. But this goes into it in detail. Plate tectonics, and these type of videos are a dime a dozen. You see these intro videos with the plates moving about the surface of the planet, you know, they're just moving around, doing their thing. You see mantle convection pushing the plates and subduction going down, you know. Rifting areas are divergent boundaries. Subduction areas are convergent boundaries where plates pass along one another. Those are transform boundaries, and I am going to talk about all of these, but not as you would to a 10th grader. It's going to be a little more complicated than that. I am going to go over some technical stuff. There will be maths involved later. I'm just going to show you, like I'll show you how angular velocity and linear velocity are very closely related, but I'm not going to take you through any examples. This would be way too long at that point. But anyway, I'm going to get into the outline of this video now, and then we're going to get into the video. Okay, let's put this definition right here for right now until it needs to be moved. This is the definition of plate tectonics. There's my source. I put it into my own words a little bit. This is the definition I'm going to be using throughout the video. I put a poll up on social media and asked you guys what you wanted me to do. You picked plate tectonics. Be careful what you wish for. You just might get it. This is going to be a long one. Anyway, you saw me put the definition of plate tectonics up here. This is the definition of plate tectonics. I'm not going to read it to you verbatim, but basically you need certain things. We'll get into that in a second. But this is the basic outline of what we're going to talk about, okay? I'm going to define it and describe it. I'm going to show you what it is. We're going to talk about the interior of the Earth and its properties. What I mean by, we're going to go all the way to the core. We're going to talk about compositional versus mechanical layers, stuff like that. 3, describing and predicting plate motion. This is a good one because we're going to talk about, and I'm going to put some equations on the board here. We're going to talk about angular versus linear velocities and how those two are kind of related, because there's something you need to understand. And many of you may have heard that maths is the language of numbers. All right, well, there's different dialects, and some things kind of can be used to describe other things, if you will, and we'll get into that because Euler is poles. We're going to talk about Euler Poles. Some North Americans pronounce it Euler, but it's German. In German, EU equals the oi sound in English, okay? So it's technically Euler Poles, but sometimes I may screw up and say Euler. I apologize. So we're going to be talking about those as well because those are very crucial to plate tectonics. And then we're going to touch on non-plate forms of tectonics. What does that mean? Well, basically, any form of tectonics is a side effect of a planetary body losing its internal heat. That drives tectonics. On Earth, it's plate tectonics. On every other rigid body in the solar system, non-gaseous world, it's not. All right? So, plate tectonics, I'm not going to read that for you, but there are certain criteria you need for plate tectonics. You can't just because you get subduction or you get the crust in lithosphere, which I'm going to talk about. The crust and lithosphere function as one unit in plate tectonics on Earth. So sometimes you might just hear me say lithosphere, and I'll get to that when I get into this part. But basically, just because you have the crust and lithosphere going into the planet and have some sort of mantle, crust, lithosphere, well, the lithosphere is technically the upper mantle, but just because you have some sort of mantle, crust, recycling, doesn't mean you have plate tectonics. This is plate tectonics, okay? And kind of, in an ideal situation, a rigid body like this, you see a soccer ball, you see hexagons and pentagons here. Ideally, on a spherical body, those make good. These would make good plate boundaries, these edges. Well, Earth isn't perfect. Things are not homogeneous. Plates do not fit these. But you can have small ones like this. I mean, plate tectonics doesn't say the plates have to be a certain size. All right, get that out of the way. But I mean, we look at the Pacific plate, and it kind of looks like an assemblage of some of these shapes. So we do kind of have those shapes. So the surface of the rigid body has to be divided into plates. It doesn't have to be hexagons and pentagons. So you have to have, in plate tectonics, you have to have that rigid outer shell. And it has to be broken into plates. The plates themselves, or fragments, of the crust and on Earth lithosphere, but on another planetary body that has plate tectonics, the lithosphere may not be involved with the crust. On Earth, the crust and lithosphere work as a single unit involved in plate tectonics. But we'll come back to that. They're independent horizontal motion. They need to move horizontally about the surface, all right? And yes, you do get subduction and they get pulled back in, but the plates themselves move horizontally. You don't get plates getting directly pulled down into the mantle. That's something called stagnant lid, and that's this. And this is key, where each plate moves about an axis of rotation. An Euler pole, or Euler pole, which we'll talk about when we get down here, and I'll demonstrate that to you better. So you need, the plates not only need to be moving horizontally along the surface, levelly, they need to follow Euler poles. We'll get to that when we get to that. And a rigid lithosphere / crust is necessary for plate tectonics to occur. I've already talked about that. If you have a magma ocean on the surface of your planet, there are no plates to move horizontally, and you don't have plate tectonics. All right, so that we've gotten rid of the definite part. Now we're going to talk a little bit about the interior of the Earth. The Earth is basically divided into what we call compositional layers and mechanical layers. Compositional changes are basically where you have different minerals and chemicals at different layers within the Earth. All right, we have 3 compositional layers. These are our basic 3 compositional layers. I'm going to try to keep this as simple as possible. If there are more, I will be leaving them out. I don't want this to be 7 hours long, okay? So we basically have a crust, a mantle, and a core. And what you can see here is you can see the relative depths. You see the surface of the Earth, the crust, the mantle, the core. So each one is separated by a discontinuity. A discontinuity is where seismic velocities change. We're going to come back to seismic velocities because they're important and they tell us certain things about the interior of the Earth, especially about the stuff we can't see. We actually do have bits of the mantle at the surface called ophelites, but it's the lithosphere, all right? And so the lithosphere is part of one of those mechanical layers. Our mechanical layers are layers that move according to the physical properties, density, buoyancy, stuff like that. Is where compositional has to do with the minerals and chemicals. And why I say chemicals and not just minerals is because in order to be a mineral, you have to be a solid. And there are 2 places on Earth where we do not have solids on Earth, all right? But we'll come back to that. So now we're talking about mechanical layers. But first, you say, oh, continental and oceanic crust. Why are these in between? Well, because they're kind of are. They are compositionally separate. Most continental crust is what we call, it's made of felsic minerals, light-colored minerals, minerals that are light in density. They make up the continental crust. This is why the continental crust does not get subducted back into the mantle. Okay, oceanic crust is more mafic, your basalts, stuff like that, and that does get reabsorbed into the mantle. All right, there are special situations where the continental crust can get partially dragged back into the mantle, but those are talks for other times. Essentially, it doesn't, and that's a key thing to plate tectonics, is the continental crust just sort of moves about the surface of the planet while the oceanic crust gets recycled into the mantle. It doesn't happen in other tectonic forms of tectonics, which I'll talk about at the end. But the lithosphere, which is also the upper mantle or top mantle, and like I said, the asthenosphere is also often referred to as the upper mantle. These three together mechanically form our plates in our plate tectonics. With this, remember I said that there were two liquid bodies, if you will, on Earth? This is one. Oceans. Water is important in plate tectonics because part of it does come down into the lithosphere back into the mantle before being returned back to the surface in volcanic activity. And it can form a lubricant on plates. So oceans are our first liquid part of the planet, but they don't make up a huge volume of the surface of the Earth. You take they're big to us. They cover 70% of the surface, but the Earth is a three-dimensional object, right? It's roughly a sphere, and this, the oceans are nothing compared to the rest of it. Okay, what you see here is this is a cutaway next to the compositional and mechanical layers. You see you have the continental and oceanic crust. I did not put ocean on there, but it's also on there because it's too thin to actually show up. Down you see the relative average depths. These depths are not perfect level boundaries. They do vary a little. But surprisingly, the lithosphere, there is topography at the bottom of the crust, bottom of the lithosphere, and all these other layers, but the topography at the bottom of the lithosphere is strikingly only a little bit more than it is from the deepest ocean trench on the surface to the tallest mountain. Right? And the reason for that is because of the horizontal plate motion. The lithosphere is getting thicker, all right, over time as the planet cools, but it's not getting like blobbily thicker. Like, under the continents it is a little thicker, but it's not like it's like 10 times thicker in one area than it is another area or anything like that. And then you can see here we have our Asthenosphere or Asthenosphere, some people pronounce it. That is also part of the upper mantle. That is a place where convection is suspected to occur, and I'll get back to that. We have the mesosphere, and then the core is two parts. We have an outer and an inner core. The outer core is the second part of the Earth that is liquid. This is solid. This is solid. I can't stress this enough. The mantle, which is bounded by the Moho discontinuity at the top and the Gutenberg at the bottom. Moho is just a shortened version of this word. The mantle is a solid. It is not a liquid. It is not a magma body. Magma is a liquid. I've heard Earth scientists get this wrong. The mantle is a solid. Well, how do we know it's a solid if all we ever have are little slices of this part of it on Earth's surface? One word: seismology. Okay, seismic waves. Whenever there is an earthquake, energy is released. Waves propagate through the entire planet. All right? Most earthquakes on the Richter scale, which most of you have heard of, 3 or less, you don't even feel they happen constantly. No one notices. They are concentrated along plate boundaries as well. Subduction areas mostly, not in spreading centers, which we'll talk about here in a minute. Earthquakes generate seismic waves, and there are two basic types, and we're not going to talk too much about them. You have P waves and S waves, primary waves and shear waves, or secondary waves. Primary waves go through anything. Talking to you, I am generating primary waves, all right? So they go through liquid, solid, gases. It doesn't matter, but there needs to be a medium of transportation, like they don't propagate through empty space. S waves go through solids only. So when we have an earthquake, and you'll have seismic stations on different parts of the planet that will pick them up, get you your arrival times, well, waves move faster through denser materials. Okay, generally they do. Basically, you have an earthquake somewhere near the surface of the earth. The seismic waves go through, the primary waves go all the way through. The shear waves will not go through a liquid, and you will have other stations throughout the planet picking up the arrival of these waves. They create shadow zones. That's how we know the outer core is a liquid, because S waves do not go through them. S waves, shear waves, need something to shear to propagate. Liquids don't shear. It's just a physical property of liquids. So S waves will not go through them. They go straight through this. No problem at all. All right? S waves go right through the mantle. So the mantle has to be solid. Okay? And we're going to get into mechanisms of plate tectonics here in a minute. But you might have been taught that mantle convection drives plate motion. It's a part of it, but it does not drive it. And you can convect a solid. I'm going to show you a demonstration here in a second of how that's possible. But the mantle is a solid, all right? S waves do not go through the outer core, but primary waves, which go through everything, will go through a liquid, and as they hit another solid, some of them will be translated into S waves again, and we can pick those up, so we know the inner core is a solid. That's how we know the general properties of the inside of the Earth, and we can run experiments to figure out the mineralogy, and it turns out the reason why these are compositional layers is because you have a mixture. The crust is felsic and mafic minerals, dominated about 50-50 for both, for all intents and purposes. The mantle is mostly mafic. It is silica rich, but that's a different, we have bonded. And the core is mostly nickel and iron. Okay, both the outer and inner, although there's probably a lot more sulfur in the outer. Here we have the driving forces, mechanisms of plate tectonics. There's three: slab pull, ridge push, and convection, which occurs within the mantle, which is a solid. Steve, how does convection occur within a solid? Well, the lithosphere and crust is rigid. I'm going to show you how something can be both plastic and rigid. In geology, we talk about two types of deformation. We talk about brittle and ductile. And I'm going to demonstrate both of those for you. I'm going to first demonstrate ductile deformation. This is a piece of silly putty. All right? If I pull it slowly, it deforms. Okay? Keep doing that, and it deforms. That was ductile deformation. What happens if I pull it quickly? It snaps. It breaks. See where it broke? Okay? And this is a solid. We define solids in geology, or how I'm doing it here, is basically something S waves can travel through. If an S wave can move through it, it's a solid. Yes, other people define solids different ways. I get that. But you can't have S waves move through something that's not a solid. But the mantle's a lot denser. It's a lot harder. It's not exactly like this, but this demonstrates to you how you can get ductile deformation in solids. And we know this happens within the mantle as opposed to the crust and lithosphere, because the crust and lithosphere is where almost every earthquake occurs. There are a few exceptions to this where plates meet and subduction occurs, which slab pull here in a second. Subduction, you can get some deeper, okay? But the vast majority of earthquakes are within the lithosphere and the crust. And there are none in the mesosphere. So in the lower mantle, there's none. So that tells us it behaves plastically. It deforms ductily, if you will. Okay, there's no brittle failure. In order to generate an earthquake, something's got to break. You don't generate earthquakes this way. You generate them from breaking something. The other things that can generate earthquakes, not just along plate boundaries, but those are talks for other times. Our mechanism, slab pull. What is slab pull? Slab pull is actually the major driving force of plate tectonics. I'm going to get rid of this here in a second, but I want to talk briefly about it because I need to draw it to demonstrate. Ridge push is kind of a side effect of this slab pull, and this helps push plates along, both of these. The side effect of these two is mantle convection. So mantle convection seems to be driven by the crust and lithosphere. So plate tectonics, unlike other forms of heat, now the Earth is slowly losing its heat, mostly in the core, through primordial heat and radioactive decay. That heat does get transferred to the surface. It is enough to convect the mantle, just not to drive plate tectonics. So in order to get that mantle to convect, to move the plates, we need a surface component, gravity convection, that drives that mantle convection, that keeps that conveyor belt going, keeps those plates moving about the surface of the Earth until they hit a subduction zone and the oceanic plates and lithosphere get recycled into the mantle. So it is dominantly a gravity-driven system. Well, what do I mean by gravity-driven? Okay, so here's a slice through the Earth. I'm going to use this with a combination of graphics. This basically is my continental crust and lithosphere. I'm combining the two. The black of my oceanic lithosphere and crust. I did not add oceans, but we need them because they are important. Okay, so there's my oceans. This is not to scale. The oceans are not this thick. Continents are not this thick relative to the thickness of the Earth. You've already seen the diagram showing you the actual thickness in kilometers. This is my core. This is my lower mantle. So my lithosphere and upper mantle, I'm going to refer to the lithosphere as the upper mantle. My lower mantle is the asthenosphere and the mesosphere. And we're going to develop and draw things here. But basically, what is a gravity-driven system? So basically what happens is our ridge push area, this is our ridge. This is where, like the Mid-Atlantic Ridge, the East Pacific Rise, these are what we call spreading centers, okay? You have three types of plate motions at the surface. You have spreading centers as one. That's where the plates are laterally moving apart. And remember I told you the mantle is a solid, and you're like, Steve, but I've seen videos of magma coming up. Yeah, that's that ridge push. As convection is driven, you release pressure off the top in the asthenosphere. And our asthenosphere is roughly, we'll just say, this is the border. Remember, it's a mechanical layer. So technically anything that passes through these layers becomes part of that. Like the crust gets subducted into the asthenosphere, but once it reaches the asthenosphere, it's essentially part of the asthenosphere because that's a mechanical layer. It's not a compositional one. As you release that pressure at a spreading center, you will get, the rock will melt, because if you do things like add water and reduce pressure, it'll melt. And you get these magma that rise, causing your plates to move laterally, right? But that doesn't drive the convection. But it's important because as new stuff is created, so generally from a spreading center out away from it, as you can see in these USGS diagrams, they're color coded here, you can see that the red areas are along the spreading centers. That's your youngest crust. Red, orange, yellow, green, and blue. Blue is your oldest oceanic crust. So this is older than this. This is our oldest, this is our youngest. And as it gets older, it thickens. Our lithosphere and our crust thickens. And at about 80 million years old, it stops thickening. But it's cold, it's denser. It's not as buoyant. So even if I had no plate boundary here, my older crust is here. It's going to form a subduction zone. Just based on gravity alone, we will get subduction. Our oceanic plate lithosphere gets returned to our asthenosphere. That's what's going on here as well. It doesn't have to be ocean-ocean. It can be continent-ocean. And the continent will move along this way. Once the ocean plate starts subducting, the continent will not subduct. All right? It will stay along and it will move. The continent will move along top of this until this plate is consumed. And that's happening right now in the west end of North America. So North America may rift in a north-south manner as Africa is doing on its east side in the East African Rift. It may be. I mean, the Basin Range province in the American Southwest is an active extension area. The East Pacific Rise, which North America is slowly moving over, is a spreading center. Now, usually when that happens, when a continent moves over, like you know, here, let's get rid of this for a second. You have a spreading center. You know, you're getting a spreading center here, and as your continent moves over it, it'll shut that off. But the East Pacific Rise, that spreading center on the west end of North America is spreading at a lot faster rate than this. Why is that? Because on the other side of the Pacific, we have slab pull and we have really old ocean crust being subducted into the mantle at a lot higher velocity. And even though the lithosphere and crust are rigid, they can behave somewhat plastically. We have slab pull here that's pulling that Pacific plate down really fast. So we have slab pull, which I've already talked about. We have our ridge push, which is caused by depressurization of the asthenosphere. And that drives our mantle convection currents. The question is just the asthenosphere convective, or is the whole thing? Well, there are two plates on Earth where the lithospheric crust has reached our mesosphere. Most seem to come down into the asthenosphere, and then they kind of level out, and then they get reincorporated into the mantle, because ultimately these will get reincorporated into the mantle and recycled. So we do have evidence of total mantle convection. This is pretty messy looking. So our plates probably has a lot to do with how well and how fast the linear velocity, which I'll talk about later, the plate, subducting plate, to see if mantle convection is going to be deep or within the restricted to the asthenosphere. And if it's deep like this, it may do things like, here's our core mantle boundary, Gutenberg discontinuity. There's something here called a D layer. Layer of the Earth with the most topographic relief on it. Makes the surface and anything else look like child's play. This may cause, you get this cold, this may cause this to lose pressure a little bit as it's recycled down. And you get bigger magma plumes, and so you get your hot spots. You get like Hawaii in the ocean. You also get Yellowstone, so this can happen on continents as well. As a plate subducts, and this is important, as a plate subducts, with our continental situation here, you will get melting because water will be introduced here a little bit. You add water and release pressure, you get melting, you get magma, and you get volcanoes. And the same thing happens over here. Okay, so I've talked about spreading centers. I've talked about our subduction. Sorry, I didn't say that. The subduction is a good sign of plate tectonics, but there are other ways to get the crust into the mantle without plate tectonics in operation. You can subduct things down without plate tectonics, and that's for the end here when I get to that. And the third one we're not going to really talk about much. You have transform boundaries. Okay, those are lateral. I've talked about faults before. You have basically three types. You have a normal fault, which happens through extension, something like this. You have your normal faults. This is just a generic cross section, scale doesn't matter. Formed by extension, lateral movement of the earth, and this block drops down relative to this block. And then geologic cross section, that's what you would draw, and that'd be your fault, those would be your arrows. A reverse fault forms from compression. So this would form reverse faults. Okay? When this block moves up relative to this block, okay? And if it's shallow enough, you get what's called thrusting, like in the belt supergroup area out west and in Canada, you get this moves up relative to this. So that's reverse. And these are cross sections into the earth. Our third boundary that we're not going to really talk about here, but this is what is happening at San Andreas Fault in California, which I'm sure you've all heard of, are transform faults. This is also a cross section. This is our fault. There is no vertical movement. Depending on which way it's left or right lateral movement, the plates are either moving away from you or towards you, but it can be vice versa as well. So in a cross section, it's hard to draw it. So in a plan map view, strike slip fault, say we have, this is just an island, a strike slip fault running through it. In a map view, this part of the island is moving past this part of the island. Okay, that's a transform boundary or strike slip fault. So that's how those relate to this, and I don't have any on here, and for this discussion they aren't really relevant. We are talking about plate tectonics as a whole here, and how they are recycled into the earth and how they move about the planet. But we will come back to this. It's just for this part it's not crucial. We talk about Euler Poles, transform faults are going to be key. So jumping back to the surface of Earth for a second here. Basically, this slide here, it's from the USGS. All my references that aren't referenced on slides or anything will be referenced at the end. I always do that. But here you have your plates, you have your divergent, your spreading centers, which are red. You have your green convergent or subducting, okay? And the teeth are on the part of the plate that overrides. So one oceanic plate will stay on the surface while the other gets subducted to the mantle. The teeth point back to the plate staying on the surface. Then you have your transform, which is blue here. Now, what you see here are the plate velocities, okay? And here is the East Pacific rise. This is that spreading center. And you can tell the velocities in some places are pretty fast, but if you were to average them all, since they are technically rigid, if you were to average actual subduction rates throughout the entire plate with its corresponding spreading center based on Euler rotation and that kind of stuff, which we'll get into here in a few minutes, it would the net effect would essentially be, it would all even out. You are going to see graphics depicting two things, angular velocity and linear velocity. Well, linear velocity is basically speed of something moving in a straight line without curving or turning, okay? Angular velocity addresses the turning, but angular velocity is related to linear velocity, and the two are, I don't want to say they're the same, that's not true, but when you look at plate motions, they're usually in millimeters per year, centimeters per year, meters per century or something like that. Those are linear velocities. Angular velocities are things like RPMs. That's probably the one most people are familiar with. I'm going to show you how arc length, because on the surface of a sphere we deal with arc length. If I was to sit here and get these 2 points on the sphere, and tell you, well, what's the most direct line on the surface, which would form a great circle, it would form here, right? But we're going to not just talk about, because we're not just dealing with great circles. When I start talking about transform boundaries, those are not great circles, okay? So we can describe those points as linear velocities, especially if we're dealing with stuff that's that tiny, okay? Okay, most of you are familiar with this equation. Distance traveled equals the rate at which you're traveling multiplied by the time. Velocity is a vector quantity. A vector is a quantity of both magnitude and direction. So I'm going to show you how linear velocity and angular velocity kind of relate. If you solve for other quantities here, you know, if you need your rate, you need to get rate alone on the side of the equation, so you would divide by your time. This would cancel out, and you would essentially get your distance over your time is equal to your rate. You know, linear velocity, you know, like our friend the Dalek here is showing us, he's moving along a flat surface in a straight line, and then he hits something. You know, that is linear velocity. But as I showed you, even on a curved surface, which the Earth is, you have point A, point B. You're not traveling in a straight line on a non-curved surface, but you can describe it that way between A and B. Your angular velocity is related to your distance velocity, because when we're talking about going in a car ride over a long distance or on a plane, we don't sit there and use angular velocity. We sit there and, you know, if we're trying to figure out our speed, we use kilometers per hour, miles per hour, which is linear velocity. So the two are closely related. I'm hoping this is making sense. I'm going to mathematically show you how they are related, and that's going to come into our Euler Poles. But this distance here along the surface of our sphere is our arc length. S will equal our arc length. Okay? I do have to look down on occasion to see what I'm doing. So that's always going to equal our arc length. It does not equal speed. Arc length, okay? Is our velocity times our time. Now we're going to talk a little bit about angular velocity. I'm going to show you the equations for that here. Our angular velocity. This is not a W. This is a lowercase omega. Capital omega is this. We're not using that. We're using our lowercase. Theta is always going to be the same thing, radians, and this is time, okay? So this is angular velocity. Okay, so that's our angular velocity. This is our linear velocity. But so how are all these things related? And I was going to go into deeper length here, but I think I'm just going to sum it up relatively quickly. You're going to have to trust me on this derivation, all right? This is a first derivative velocity functions thing. It's calculus. If you want to know more detail how these things are all kind of the same thing, go to CalcWorks. There's an excellent lecture on it. It's linked below. It took me a while to find it. She explains it 1,000 times better than I do. All right, so here's our original, you know, equation: distance equals rate times time. All right, translate it there. And you can see our arc length, angular velocity, linear velocity. So we solve for V. Well, how do we solve for V? We divide by T, and those cancel. Oh, S over time equals our V, okay? Another way to write that would be just to do our velocity equals our arc over our time. Our arc length, S, okay? We have that here. S equals this. So we could substitute this here. So we have V equals times our theta, which is our angle, radians in radians. You can translate radians into degrees, because you're going to see later when I talk about Euler Poles, we're going to use degrees. All right, but I won't get into any detailed maths. I'm just showing you how these things are related, and then I'm going to talk about how they're different and why we use both, but we're kind of describing the same thing. Okay, so we get that, but we still need our time. We swapped our arc length for this. I'm going to rewrite it. So our velocity is our rate theta over time. Okay, so that is just that rewritten. And since this right here is equal to this up here, that is that. It's our angular velocity written right there. We can swap out our theta over our time for our W, our radians. So we get our velocity equals rate times our omega. So we can swap that for that. And this is our linear velocity. I think that's explained correctly, but that's how they are all kind of the same thing. Now, when you see me talk about angular velocity and linear velocity in Euler Poles here in a few minutes, I am going to talk about them as separate things, right? The angular velocity, when something moves, say you have the axis of the Earth, okay, right, and it's rotating. The angular velocity could be measured in RPMs, radians per second, degrees per hour, which is 15 in this case, or RPMs, which is ridiculously low because the Earth spins once every 24 hours. But the angular velocity, nothing changes, all right? The angular velocity, say I'm at 15 degrees per hour rotating, is the same at the equator as it is all the way up here near the axis of rotation, okay? That doesn't change. It's 15 degrees no matter where I am, all right? However, our linear velocity changes. Essentially, if I'm spinning here, and this is my North Pole, at the equator, to cover that angle, that 15 degrees per hour, I have to move faster, okay? But to cover the same amount of 15 degrees near the pole, I'm practically not moving. And at the pole, I'm not. So that's the difference. Linear velocity is a measurement essentially of speed, you know, and we're talking about plate motion, we're usually talking about millimeters per year, centimeters per year, or meters per century, something like that. That when you see that, that's what they're talking about, linear velocity. When you see things like moving around an Euler pole, you know, to move in X amount of time, it moves 10 degrees or 11 degrees or whatever, you're dealing with angular velocity, essentially. All right, so basically you have a sphere, okay? And we'll say it's the Earth. This is your North Pole, 23.5 degrees tilt, all right? The Earth spins once, 24 hours, counterclockwise relative to north, once on its axis. The Earth rotates for once. 360 degrees, one time in one day, all right? For all intents and purposes, okay? Now, Euler Poles, Euler was a calculus master. He came up with so much stuff, but we're just going to deal with Euler Poles. This is an Euler Pole, okay? It's just the entire planet moves. The solid inner core does not. It moves at a different rate than the mantle and the lithosphere and the crust, and the outer core is just a churning bubble of relatively consistent convection, as where the mantle is not, and has all sorts of miniature convection cells because it's a plastic solid. But anyway, so that's basically that. But so the North Pole is an Euler Pole, but plates move along these as well. But plates are fragments of the bigger thing, right? So you know you have plates on a spherical Earth divided out. So let's put another one in here. I'm going to show you a good demonstration here in a second of the graphic. But these plates at spreading centers might be moving apart. At subduction, They are moving together. And we'll just say this is the subduction. So we have our subduction here, here. And we have moving apart here, here. The rate at which these plates are moving at any point is their linear velocity, like you've seen on that slide showing centimeters per year. So they move at their linear velocities on the planet, but they rotate via Euler Poles. Now, Euler Poles are not matched up to the North Pole. They don't need to be. Nothing like that. And quite honestly, plate tectonics is a really bizarre way for a planet to lose its internal heat. And we don't really know why Earth uses plate tectonics or what's required for plate tectonics. Likely, it has to do with composition. Obviously, you can't have plate tectonics on a gas giant. So composition plays a role, and different mineral ratios may as well. Heat flow probably does as well. You know, plasticity of the mantle, stuff like that. But what may also play a key role is mass. Earth is the only rigid body, terrestrial body in the solar system to use plate tectonics. It's also the biggest. Is that a coincidence? I don't know. Earth may be at the lower limit for a plate tectonic regime to happen. And it could be a large moon plays a part as well. There's no real way to verify that. We can describe these plates moving based off Euler Poles. This plate is coming around the planet this way and it's riding over the two subducting plates, okay? I'm not going to put continents on here or anything, it's not necessary. That plate is moving essentially as one rigid body, all right? Which means it has to be rotating about some axis. So somewhere on the opposite side of the planet is an Euler pole at which this plate is rotating this way around. Here, same thing. This thing is moving, we'll just say the Euler pole is here on this one, at which way the plate is moving. And this isn't a perfect representation. I didn't plan this out ahead of time. I have a graphic to show you exactly how this happens. But how do we find these Euler poles? And plates can have multiple Euler poles because plates aren't perfect. Within the interior plates, they will often have multiple Euler poles because what happens is you get those transform faults I was telling you about. Stuff starts moving laterally. And as that happens, the interior of the plates might crack a little and buckle. The plate's still moving as a whole, but this area is compensating for stresses, multiple stress fields, okay? So it might not move as rigidly. We call these microplates, and these are talks for another time. The Earth itself is divided into about a dozen very large plates, and actually the two on the west end of South America and North America are actually the same plate. They're just almost been consumed by the underneath into the mantle. We just give them different names, but anyway. So you get these microplates developed, and that's a talk for another time, but these transform faults, these start to form perpendicular to Euler Poles. Okay, so this is just basically, I'm showing you how this works. You get your transform faults, okay? They form here. Let's make this our North Pole. That's our axis of rotation, not our Euler. Sorry, that was my bad. So we get these transform faults as these plates move about the globe. Places will start to fail laterally. Well, we can use these transform faults, take them up perpendicularly if the linear velocities are the same and the angular velocity is the same. But since this is a spherical object, at some point they're going to meet. That's going to be our Euler pole. Okay? I hope that made sense. But fortunately for you, there's a great graphic on this. The people who made the slides I'm about to show you demonstrate this awesomely on a 3-plate model. You need a minimum of 3 plates to get this to work really well. And the Earth has over 12, so we're good to go. The relative motion between 2 plates is described by a rotation, our Euler pole. The transform faults, which I just showed you across the surface, are aligned along circles whose centers define the axis of rotation, the Euler poles. And they're perpendicular to that axis of rotation on a 2D model, we can model them as being perpendicular. They're not truly perpendicular. I'm just saying that for brevity. On the sphere, in order to find your Euler pole, you look for your transform faults, and you follow the surface this way or this way to locate your Euler pole. That's what I mean by perpendicular. Obviously, we're dealing with spherical geometry, so that's not exactly perpendicular. Then you take a bunch of them, and you find them, and that's how you find your Euler pole. Okay, so the linear velocities vary within a rigid plate, which is our lithosphere and our crust. The closer the pole of rotation, the Euler pole we get, the lower the velocities. That's that linear velocity I was telling you about. When I said linear velocity changes, just like it does at any rotating object, you know, it's our rotating Earth, our linear velocities here are faster along our equator than they are at 60 degrees north or south. Those change. It's the same thing with our Euler poles because they are axes of rotation. Angular velocity, however, is constant. Just like on here, just like I demonstrated on my rotating Earth here, my little soccer ball Earth. You know, even though the linear velocity at the equator is much faster than at 80 degrees, 60 degrees, whatever latitude, the angular velocity is not changing. It's still moving at 15 degrees per hour. All right? Doesn't matter what latitude I'm in. So that stays the same. And since Euler poles are axes of rotation, that applies to them as well. So how does this look? Well, this is their most recent model. They have north on there for Earth's rotational axis, and the other pole running through is an Euler pole. And this is a 3-plate model. One is gray and essentially stagnant relative to the Euler pole. Then you see a blue and a yellow, which are moving away from one another. You see a black line with a red interior. Those are our transform faults, are aligned along circles. In this case, Euler latitudes, if you will. Just like you have lines of latitude on the Earth relative to its rotational axis, the same thing applies to Euler poles. And these are where your transform faults initiate. So the transform faults are aligned along the circles, which is basically what I just said. The circle whose centers define the axis of rotation, which I also have already explained. As the plates move away from one another, these circles, or essentially Euler latitudes, can be traced out. So you can go back in time or forward in time with them, as long as you're careful. More likely back in time, that's a lot easier to do. Because even though you can extrapolate into the future, the problem is there are other factors in play in plate tectonics than just Euler poles and transform faults, subductions. We have what's called Wilson cycles. Ocean basins tend to open and close. So now I'm going to show you these slides showing you how angular velocity, which is in degrees here, you can do radians, but you just translate it into degrees. The angular velocity does not change, but the linear velocities do, and that's what's going to be demonstrated in these next few slides. You have 0 degrees of angular velocity change, you have 11, and as you can see, the purple or red lines on the globe, you're sweeping out your linear velocities. Now, in order to keep the angular velocity consistent, as we move towards our Euler equator, we have to sweep out more distance than we do closer to our Euler pole. So from 0 degrees to 11 degrees to 31 degrees, see, it just keeps going, 54 degrees and 77 degrees. Those purple lines you can see closer towards our Euler equator, we have to move faster to keep that angular velocity consistent. And that's why I went through the whole thing with you about how angular velocities and linear velocities can be used to talk about one another, how they're similar, kind of like dialects within a language. And there are known Euler poles. Just to show you this real quick because I think it's cool. This is the plates, modern plates. The red are the youngest. I've already shown you this, the youngest ocean crust. The blue is the oldest, and it follows the colors of the rainbow, red, orange, yellow, green, blue. Now, say you had your Euler poles. I put the one for Quebec. the Afro-Euro one, and there is one in southeast Greenland. See, you can have competing Euler poles, and that's due to, you know, formation of microplates in different stress fields. Well, I just wanted to show you about rifting. What we have here is we have triple junctions, and you see what we have is we have a yellow triple junction with a purple third arm. Triple junctions I'm going to talk about briefly here in spreading centers. And the purple eventually becomes a transform fault and follows another Euler pole. And the gray one here becomes extinct. Like I talked about ridge push and how that generates rifts. Well, when you start to form rifts, rifts can fail. The Mid-Continental Rift in North America is a perfect example of this. The Gardar Rift in Greenland, perfect example of this. Rifts can fail in part or in whole, all right? But what happens is when you get the motion of your plate starts, you start to get that slab pull from wherever it is in the globe, okay? You get your old plates sagging going into the mantle. You get a triple junction somewhere, usually within a continent, but it doesn't have to happen in a continent. These specific rise is totally within an ocean plate, well, for the most part. But it usually happens within continents, and they start to rift. And eventually other arms will form along your rift, and a couple things will happen. One arm will die, and one may actually translate into a transform fault following an Euler pole, and then your rifting will occur along this. This is essentially what the Mid-Atlantic Ridge happened in the Mid-Atlantic Ridge with the breakup of Pangea. Okay, I do have a graphic demonstrating this, and I'll show you here real quick. This is just your Earth. The yellow is your North Pole. You have your red lines, which are rift forms. All right, triple junction. Now, like I said, many things can happen with triple junctions. There's different types, but those are talks for other times. So you start getting spreading. All right, like I said, that's due to slab pull somewhere else on the planet. And you get new ocean crust, which is here is demonstrated as red. That new crust moves away, becomes the yellow as new red crust is introduced, and then that yellow becomes green, that other red becomes yellow, and new red is introduced, and then that big black line up top here, we have a failure. So our rifting continues along two of the arms, and other rifts develop, and eventually they connect. And here it shows you same thing, shows you rifting. And now this white circle we have an Euler pole established as this other rifting occurs. Then another Euler pole becomes established as a couple of the arms die, and as you can see, this one up here, these two die. This one becomes a transform boundary as a new subduction zone in the middle of the ocean forms from slab pull and old crust. So we have the good establishment of our two Euler poles until something wacky happens. What do I mean by wacky? Either two continental fragments collide. Continents do not get subducted into the mantle, so eventually that subduction engine gets shut off, which means in order to get an average plate movement that's consistent, a new subduction zone is going to have to form somewhere else along an old plate. And this is kind of what drives Wilson cycles and why ocean basins rift and close this way tend to do this instead of doing this around the whole planet. We use paleomagnetic data to determine the age of the ocean floor. Now that only gets us back, until Pangea. There is some older crust in the Mediterranean, some older ocean crust from pre-Pangea that has survived, but it's slowly getting consumed. It'll be gone in the next probably 20 million years. So we use paleomagnetic data. Well, eventually the continental crust stays about the surface of the Earth. It does not get returned into the mantle. It stays at the surface of the Earth. Okay, our oceanic crust will eventually get returned into the mantle. The only exception to this will be those old flights of parts that have been jammed up on top of the continents. But 99.999% of all oceanic crust that the Earth has ever created is gone, or will be gone. That's because, it has to do with slab pull and all that other stuff, densities stuff I've already talked about. Continental doesn't. It gets so it does not get returned into the mantle. Well, if all the oceanic crust gets taken down in the mantle and the continental stays, the oceanic crust gets consumed and recycled. How do we reconstruct paleogeography pre-Pangea? That's one of my favorite questions, and it's a good one. We also use paleomagnetism of the ocean floor to determine where the continents were 10 million years ago, 20, 50, 100, 200. Past that it gets a little complicated, and we can't really do it because there is essentially no ocean crust older than that. So then we have to go to the continental crust. But wait, how do you get paleomagnetic data from the continental crust? Well, the continents have always been around since plate tectonics has been in operation. And when we get to the last part, I'll explain why we don't have old continental crust. All right. So, but what happens is the oceanic crust, as it's created and it moves away, make room for new oceanic crust, you can date that ocean floor. Well, you can do the same for the continents, but you can't just do it anywhere. You have to look for what we call dike swarms. They too will record paleo latitude and age within the continent. And this is what we are using to reconstruct the now, what is a supercontinent is talk for another time. Most people consider Pangea a supercontinent, but never in the history of Earth has all the landmass has been totally together. At best, it's been 85%, even during Pangea. Well, there was another older continent before that called Rodinia, where it was a similar situation, right? About 1 billion years ago. Pangea, about 300 million years ago. So Rodinia was a similar situation, and we have to use these dike swarms, which we can get the age of the dikes and paleo location. That will tell us, well, was the dike near a pole, or was it near the equator? Where was it in relationship to other more or similar age dike swarms, things like that. And we can reconstruct Rodinia. Okay, so we have Pangea, which we have real good reconstructions for because we still have existing ocean crust from its breakup. It formed roughly around 300 million years ago. Rodinia, we're starting to get real good. About 1 billion years ago. These are the heights of their assembly. All right, and some existed a little longer, some existed a little less, some had accretions later, some did not. You go back, you have Columbia/Nuna, they're the same thing, about 1800 MA. And Kennerland, approximately 2500 MA. Now here you start running into problems. Here these two supercontinents could be described as megacontinents, where over 85% of the land was joined together. These not so much. This may actually have been 3 smaller supercontinents. All right, we're pretty sure that is, but they were close to each other, but they never managed to move together. Columbia-Nuna might have been 2. I kind of consider a supercontinent, or a third to 2/5 is in a single landmass. That's a supercontinent. I'd call it was 85 or 80 to 85%, and I'd call it megacontinent. But anyway, talks for the time. So you go back further in time, and you don't get these massive megacontinents. Here's when we start to get into something. This is Precambrian, 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 Phanerozoic. Was plate tectonics in operation here? Most geologists would agree for these two, yes it was, because we have evidence of lateral movement of lithospheric plates about the surface of the globe. We have other things that mark plate tectonics that aren't listed here. We have passive margin sequences. You also have ophelites, Wilson cycles, things that clue us in based. We don't have really good paleomagnetic data for these two, but we're working on it. Okay, you have these things that clue us in that plate tectonics, and there was in motion, and there was active modern subduction, oceanic plates being recycled into the lithosphere. These are a key indicator of plate tectonics in motion. So we probably had modern plate tectonics in action. The lithosphere might have been a little warmer, a little thinner, or whatever. It may not have been exact. There are certain places today where plate tectonics may still not be in action. There may be remnants of a pre-plate tectonic system, but that is a talk for another time as well. But you get back to here, and you do see things like passive margin sequences, Huronian supergroups, stuff like that, in the Proterozoic. But you start to go back below the Proterozoic into the Archean, and into the Hadean. And you don't see things that you see associated with modern plate tectonics. As a matter of fact, you see things like TTGs. Basically, these are granites that are rich on the plagioclase side. We don't see them being created anymore really that much. We do see them in island arc environments. There are TTGs from the formation of Columbia Nuna in northeastern Wisconsin during the Pinokian orogeny. But back in the Archean and Hadean, we don't see any true granites. We see these. We have greenstone belts. These also are not being produced by Earth anymore. And it's real tempting to use geochemistry and sit there and say, well, we looked at these rocks from the Archean and they look like they have the chemistry necessary that would indicate the presence of water in the mantle. So there must have been subduction, active subduction, to bring the water into the mantle. No, that's not necessary. You don't need modern plate tectonics to get oceanic or continental lithosphere into the mantle. Okay, that's not a good line of evidence. All right, but with these things, these two big things, there's more, but these are the two major ones. And the fact that Earth doesn't do this anymore is a key indication that a different tectonic regime was in operation during most of the Archean up into about 3200 MA, probably with a transition to about 2700 MA. So we had roughly a 500 million or half billion year transition zone where something and plate tectonics was in operation. The Hadean, there's no plate tectonics. We can't assume that. Why? We have no confirmed continental crust of Hadean age. Some of you have probably heard of Jack Hills, might be like, wait, Steve, but we have, 4,300 million year old or 4.3 billion year old zircons in the Jack Hills. So there must have been continental crust then. Incorrect. Those zircons, Jack Hill zircons, are detrital. And I've talked about this before. That means the Jack Hill zircons are pulled from a metaconglomerate. That means they were derived from elsewhere. Conglomerates are sedimentary. Any zircons in them were taken from somewhere else, because sediments are derived from other rocks. Well, clastic ones are, and this is a clastic sediment. So something had to erode, and when it did, and when this was getting deposited, it brought with it some of those older zircons. But the Jack Hills, this metaconglomerate, people argue, but it's around. It was deposited about 3 billion years old, which would make it Archean. Okay, so we don't have it there. Okay, so we don't have actual continental crust in the Jack Hills that is Hadean in age. What I mean by continental crust is crust that was deposited as magma upwelled and solidified. So igneous rock or meta-igneous rock, because it probably would have undergone metamorphism several times. There is a place, and I cannot pronounce this word to save my life. I'm not going to try. So you can look into that on your own, but I'm not going to go into any detail on that. So we basically don't have any confirmed continental crust on Earth that has been derived directly from a solidified magma. Not confirmed anyway. So during the Hadean, and even if there is a continental fragment somewhere, that doesn't mean plate tectonics is in operation, but the fact that we don't have any, and we know that continents do not get recycled into the lithosphere during plate tectonics, we know there was no plate tectonics in operation. It's just a simple fact of the definition. So you could not have had plate tectonics in operation in the Hadean. All right. Now, there has been a proposed supercontinent that's approximately 3 billion years old, or 300 million MA, called Ur. I am not convinced that this thing even existed. But if it did, this is the first evidence of solid cratons in the world. Cratons are those stable platforms which all continents grow upon. North America has the Superior, the Slave. These things grow over time. But that one, if it did exist, we have cratons from the Archean. We do not have Hadean cratons. What else could have been in operation? here are two possible options. You have lid tectonics or stagnant lid tectonics and heat pipe tectonics. You can have a combination of these things. Already, you know, we have plate tectonics in operation on the planet, but there are small areas that seem to have an older type regime, and those are talks for other times. So nothing is ever one or the other. These are two options, okay? What is lid tectonics? Well, here's a cross section again. And you know, Earth is unique in the fact that it has massive surface oceans, which probably could have played a very important role in the establishment of plate tectonics. That too is a talk for another time. So you have your slices, your two planets. This is probably what happens on Venus, and this is what happens on Io. So basically, in a lid situation, you get mantle convection. We're just going to assume total mantle convection. All right, this is for demonstration purposes. And you also get mantle movement horizontally. But what happens is the crust doesn't move. It stays, all right? So actually don't get horizontal mantle movement. You get convection cells going more this way than vertically. That's a proposed mechanism. Don't ask me how it works. That's a talk for another time. But we'll just sit here and say you get massive convection cells with an entire mantle. What happens is your crust, I mean, depending if it's continental or oceanic, it varies a little, but you'll get your fractures, and what happens is you actually get pulled down this way. You get dragged down into the mantle as a fragment, okay? This causes magma to fill this way, creating new crust. This is not an ocean, this is just new crust. And magma will eventually, that there will force a rift somewhere else and more magma to fill here. This doesn't really produce continental crust, right? This is good for an ocean regime. You can also get something that's called underplating, where you get the magma will rise up and just build and build and build under here until the lithosphere gets so thick relative to the surrounding lithosphere that it subducts back into the mantle. So you get really thick lithosphere forming over time, like you would on plate tectonics, but instead of forming a subduction zone, this happens. So you get lithosphere, like I said before, in modern plate tectonics, our lithospheric plates do not have a lot of topography on the bottom of them as they could. And here you're talking a lithosphere that in places could be 50 kilometers thick, in other places it could be 400 kilometers thick. Okay, so that is one regime, and basically you would have something that would be broken off into plates, something like this. But that's not plate tectonics. You would have fragments, but they're not moving horizontally. What's happening is, say the blacks, pentagon ones, they're being drawn back into the mantle, and the white ones are being pushed up, all right? And eventually, this would cause a formation of a continental crust. As you get more felsic minerals coming up, you could get continents and initiate plate tectonics. Heat pipe is how Io loses its internal heat. Basically what you have, and this is what may form hot spots on Earth. Hot spots are probably a form of heat pipe. It's a remnant, but it happened. You get melting down here near the core, and your magma rises and rises. And instead of plates, because you don't have plates, you have a stagnant lid like you would here. What you get is you get volcanoes, and they explode. And what happens is they get bigger and bigger, and eventually they get so big that they shut this off here. So your heat pipe is forced to move somewhere else and start the process again. And there is no mantle recycling per se. What eventually happened was, this would get thicker and thicker, and as it gets down into the mantle doesn't convect that well, if at all. But if it does convect, what happens is it would just get reincorporated back into the mantle slowly. Right? It doesn't get pulled into the mantle through gravity. It doesn't get pushed down through the mantle like it does here. It just generally gets reincorporated. So those are two types of tectonics that are not plate driven. And these are internal heat driven. These are core mantle driven. As we're modern plate tectonics, yes, the core and mantle plays an important role, but it's surface driven. Pull slab, gravity, convection. Anyway, that's it. That was really long. If you have any questions or comments below, please leave them, and I hope you learned something.